Hello, and welcome to Kognito Key. Today, we're going to dive into something really interesting, the secret life of magnetic circuits. We'll look at the battle between those perfect diagrams you see in textbooks and the messy, fascinating reality that engineers have to work with every single day. You see, on one side, you've got this clean, predictable path that magnetism is supposed to follow. But on the other, you have this chaotic reality where energy just doesn't want to play by the rules. It's these so-called imperfections that we're going to break down today. So let's start in that perfect world, shall we?
All right. First, let's just imagine a perfect universe for a moment. In this ideal world, we have something like a solenoid. We pass a current through it, it generates a magnetic flux, and every single line of that flux stays neatly tucked inside the core, following the exact path we want it to.
Now, this perfectly behaved energy is what we call useful flux. You can think of it as the hero of our story. This is the flux that does all the real work, spinning motors, transforming voltages, all the important stuff. It's efficient, it's predictable, and, well, it's almost completely theoretical.
As you've probably guessed by now, the answer to that is a big, loud no. The real world just isn't that neat and tidy. And that one simple fact opens the door to two incredibly important effects that every single engineer has to understand.
So, the first of these imperfections is called leakage flux. Honestly, the best way to think about it is like a leaky pipe. No matter how good your plumbing is, a little bit of water might still escape, right? Well, it's the exact same idea here. A magnetic circuit is never perfectly sealed, so some of that magnetic flux will always find a shortcut and leak out of the main path. And this is our leakage flux. It's the flux that kind of goes rogue. It doesn't travel through the core to do any useful work. Instead, it just loops through the air around the coil, contributing absolutely nothing but inefficiency. It's pure, wasted energy.
So when you put it all together, the math is actually pretty straightforward. The total flux that your coil produces is simply the good, hard-working, useful flux plus this stray, rebellious leakage flux. It's a really basic but absolutely vital piece of the whole puzzle. Okay, so if we have this leak, the first question an engineer is going to ask is, how big is it? We need a way to actually measure this inefficiency, and for that we have a very specific tool. It's called the leakage coefficient, or lambda. And the beauty of it is just how simple it is. It's just the ratio of the total flux we're creating to the useful flux we actually get to use. You see, in a perfect circuit, this ratio would be exactly 1. But in the real world, it's always greater than 1, giving us a clear, solid number that tells us exactly how much energy we're losing.
But leakage isn't our only problem. There's another strange little effect we have to think about, and it happens right here, in the air gap between two parts of a magnetic core.
This effect is called fringing. Just try to imagine the flux lines being forced to leave the comfort of that metal core. As they have to jump across the air gap, they don't just travel in a perfectly straight line. They actually repel each other and bulge outwards, kind of spreading into the space around them. And this definition here really hits the nail on the head. Because those magnetic flux lines naturally push away from each other, they spread out the moment they're not contained by the core anymore. This bulging or fringing, it might look subtle, but believe me, it has some major consequences for how the circuit performs.
And this breaks it down perfectly. So, first, because the flux spreads out, the effective area of the air gap actually becomes larger than its physical size. And second, since the same amount of useful flux is now spread out over a bigger area, its concentration, or what we call flux density, goes down.
And here is a critical rule of thumb to remember. The wider that air gap is, the more dramatic the fringing effect will be. So a small, tight air gap will have less fringing, while a longer one will cause those flux lines to bulge out a whole lot more.
So, we have leakage and we have fringing. And you might be sitting there thinking, okay, but are these just minor details? Why can't we just ignore them and stick to our simple, perfect models? Well, because in the real world, these effects are the difference between a design that works and one that fails. They are like a constant tax on efficiency. If you're designing a motor, a generator, or a transformer, and you ignore leakage and fringing, I can guarantee your calculations will be wrong, and your final product will definitely underperform.
And this really leads us to the big challenge for engineers. Now that we understand what causes all this leakage and fringing, how do we fight back? What choices in materials, or in the shape of the core, or in the size of the air gap could we make to minimize these effects and build a truly efficient machine?
I really hope this explainer helped demystify leakage and fringing for you. If you found it useful, a like is always so appreciated, and please be sure to subscribe to Kognito Key for more deep dives into the fascinating world of engineering. Thanks for watching.